for our next step, that is the snappy hex mesh step. So for that, we are going to try different configurations of this file, snappyHexMeshDict. So let's start. Let's open first that documentation of snappyHexMeshDict. So basically, a snappyHexMeshDict can do three things. It first can perform a castellated mesh. Then what is this? This basically what it does, it takes our mesh, that is the, let's open it, our big mesh that we created with BlockMeshDict, and places over this all the STLs we loaded with surface feature extract, so that it subtracts, it only keeps the cells that are inside this structure. Okay, so we are working here. Let's try the simplest case. We are just working with castellated mesh, so it is set to true. So it's going to execute the command for castellated mesh. As you can see, snap and add layers are set as false, so they are not working. So let's start trying to understand this file. So first, we are presented here with geometry. What this does is going to read and set the names of our outer geometry, our boundaries, let's say. Okay, so here, for example, it reads atmosphere STL and gives the name to that patch, to that face. It doesn't need to be the same, but for simplicity, we call this the same. So it does the same with all the STLs we put in the try surface folder. So it does the same with the bottom STL, it does the same with the inlet, with the outlet STL, sidewalls, and wall one. Here we have some refinement boxes, so don't worry about them. We are going to use them, but later when we create a bit more complex meshes. So we comment those out. So this would be as these lines weren't there, so they are not executing. So we are only working with these 6 lines. So we proceed with the castellated mesh controls, the ones we are using as we set this to true. So I don't want to talk about this part, just leave it there. If you are working with bigger meshes and you're having problems, you can set this number higher, but it's pretty high. It's set to 200 million. It would be, but if for any reason your mesh is bigger than that, you would want to make that number bigger. But for the general cases, these settings are going to be enough. So we follow. As I told you, this is going to be the simplest case. So we have here 2 types of refinement. We have first an edge refinement that refines the edges of what features, of the features we define: atmosphere, inlet, outlet. As I told you, we created before this image file. So this is the simplest case. So all the refinements are set to level, the level 0. So we are not making any refinement. Okay. So we're going to see this later in more detail. So there is another type of refinement that is surface based. As you can see, it uses the surfaces we created. These names, atmosphere, are the names we set here. So if you put something different here, you will need to make it the same here. So as again, we are doing the simplest case: no refinement, no edge refinement, no surface refinement, level 0 to all. But we are setting here, this part is important, we are setting here the type of boundary that is going to be. So for example, for atmosphere, for inlets, for outlets, you want to set them to patch, type patch. Okay, type patch. We do the same with inlet, no refinement for outlet, bottom, no refinement. But here, as you can see, we are not defining the type of patch, but we would want to set this to wall. But this part is not necessary, because by default, this, if you don't specify this line, these patches are going to be set as walls. So it's not necessary to do it, neither for bottom, nor walls, nor wall 1 or cycles. And as I told you, the same 0 0, so there is no refinement performed. So refinement box, there is another way of refine that is based on a box we can set. As I told you, there was here at the beginning a refinement, some boxes that were set at the beginning. We are not using that now. And what else? As you can see, this what follows is this location in mesh. This is very important. We need to define here a point in our domain that it is inside the mesh we want to keep. So to visualize that, let me open our CAD. So we just need to pick a point that is inside this box. So let's draw a line, for example. That would be, let me guess. Okay, let me guess. Let's say here in x 0.5 and in y1 either. Okay, sorry, 0.5 and 1. And as you can see, we are inside. So this is a valid point. What I said was 0.5 and 1, and that z-axis is simpler because it goes from 0.52 to from 0 to 0.52. So any point that is between that interval would work. So 0.25 is okay. Don't worry about these options. And now you can see snap controls, but as I told you, we are not doing snap controls in this example. We are not adding layers. We are not using these commands. I'm going to explain them in a bit. What else? We have mesh quality controls. This is going to define. This is going to tell SnappyHexMesh if the mesh it has created is okay. So it creates a mesh with non-author on it bigger than 65. It's not going to allow it, and it's going to run it again. So it complies to these settings. So maximum orthogonality 65. You can set it to lower if you want. Max boundary skewness, max concave. These are values that are going to depend on the case you're running. So we are not going to talk about it. So our first case of the SnappyHexMesh is ready to be tested. So we close this and we go to our case file, fail case, I'm not sure how to say it. Block mesh. No, let me change this. Let me close this. I don't want to save this. Let's call this, as it's going to use only castellated mesh and no refinement. Okay, no refinement. We cannot. I know. Let's close view. Let's close the terminal and try again. Okay. So this is going to be our no refinement case. So we open in terminal WSL and we run snappyHexMeshDict. So this is going to take a bit of time, so we can make like a summary. So first we did the block mesh, then we did the surface feature extract, and then snappyHexMesh. So those are the 3 commands you need to create a mesh. Remember that we are doing an structured mesh, so everything is going to be a perfect cube. Nothing is going to be, for example, the non-orthogonality is going to be zero. So this would be like your dream mesh to work with. So let's wait for it to finish. So it finished. It took 79.13 seconds. So let's check our results. As you can see, it has been created a new folder. In this folder is our new mesh. So let's open our case in OpenFOAM. As you can see, we are in time 0.001, and we have created our domain. As you can see, all are perfect cubes. Nothing has been snapped. So, but what you want to check here is to check your boundaries. So how are we going to do that? Let's check one by one. Let's hope everything is okay. So we activate here the patch atmosphere to see if it's correct. As you can see, let me put this as surface. Yeah, okay. Okay, it is working as we wanted. We have our atmosphere layer that is at the top and in this spot. So let's check now inlet. Let's search inlet. Should be here. As you can see in green, is correct. And let's check the outlet in this side. Wait. What happened? Outlet, apply. It's not showing. Why it's not showing? Colors. Let me turn this, okay? Let me turn off internal mesh. Okay, now it's working. So we have our outlet in green. Let's check now the wall one. That is this part. Wall one, correct, perfect. Not finding that. Then the bottom. It's okay. Yeah, I changed color, but it's okay. The red one is our bottom. I changes colors, but let me turn off bottom, for example. No, let me turn on bottom and turn off wall one. Yeah, it's okay, but it refreshes the colors every time we hit, so don't worry. I was worried. So finally, let's activate sidewalls. Sidewalls are perfect. So let's run a check mesh to see the quality of this mesh. We run the command check mesh. Let me cancel this with Ctrl C. I'm canceling this because I don't want to check the zero mesh. The zero mesh is the block mesh. So let's check mesh and then set to latest time So it checks the 0.001 mesh, the mesh we want. So we wait. You can see that it complies to all the geometry checks. It has a non-octagonality of 0 because everything is perpendicular, everything is active. So let's write down the data. I don't know. So we have this no refinement case, no refinement. Let's say case. Let's put here number of cells. It is set as here 2,912,000. And number of cells. What else can we type here? The time it took is here. Time it took 79.13 seconds. Okay. As I told you, this is the simplest mesh we can create. All cubes. So let's go to the next case. Not next case, but next configuration. I don't know. So we copy our original case, and we are going to try here. We are going to try the edge refinement. So we delete this folder, the 0.001. We go to system, and we change our SnappyHexMeshDict. So as I told you, there was a part here. That not use refinement. There is a part here called explicit feature edge refinement. So what it does, it refines along the edges. I guess let's see what it does. So we are interested, as I told you, in the part of our domain where the flow is more complex. So we want to refine the border walls. So we set this to level 1 refinement to see what it does. We set that to 1. We close this. We open our terminal, WSL, and we run the SnappyHexMeshDict, and we wait for it to finish. So it finished. So let's check the results. Surface with edges, and here are the results. As you can see, this is acceptable here, and like this. It's refined in the part we want, but as you can see at the bottom, it is not as refined as I would like. But we have this case, so let's try another. But first, let me run a check mesh so we can type the stats. So this case would be edge refinement. So the number of cells. Hey, let me cancel this and check mesh again, but for the latest time. You can also check the number of cells here in information. It is here, so it's 3,201,372 cells. As you can see, now we have some non-orthogonality. 25 is an acceptable number. Not much, definitely. And if we go up, we can see that we have not only hexahedra but also polyhedra cells, and the total of cells are here. It's drying a bit. Why is that? Why is that? I don't know, but for some reason let's trust our check mesh. So that would be 2 million. No. Here in cells, 2,995,181. So as you can see, there are. Let me see. Let's do the subtraction. There are 83,000 more cells, and this took 477 seconds to run. So we close this, and we tried another type of edge refinement. So we copy this, and now we are going to do a surface refinement. So we delete this, and we go to our SnappyHexMeshDict, and let's set the language to C++, and let's make this value 0 again, and we are working now with refinement surfaces. So we just want to refine along the bottom surface, so we set the levels, the minimum level of refinement to 1 and the maximum level of refinement to 1, so we ensure at least one level of refinement. Well, for sure, at least one level of refinement. We close that, we go back, double the cell in the direction bar, and we run the SnappyHexMesh, and we wait again for it to finish. So it finished. Let's check the results. OpenFOAM. Okay, OpenFOAM. Surface with edges, and we see, well, it's similar to the what's it called? The edge refinement. And let's check the bottom. But as you can see, now it's uniform. That now is more like what we want. So you can see the difference. What is happening here? So naturally it's going to happen something like that. Right here, okay. So let's run a check mesh, and let's cancel again, check mesh, I will forget, check mesh latest time. So we are going to have here the surface refinement, and what is, well, let's see non-orthogonality 25, the same as with edge refinement, and number of cells, where is it? Here we have, as the mesh has been refined even more, we have now 3,200,000 cells. How long did it took? It took 103.45 seconds. Okay, let's close this, and now we're going to go to our final type of refinement that we are going to explain in this video. So that would be box refinement. Let's delete this, and let me open AutoCAD again so I can explain. So we have our geometry, and what we are going to do, we are going to define boxes that are going to define what areas are going to be refined. So for example, as we want this bottom surface to be refined, we would draw boxes, let's say 0.2, 0.2. Okay, so inside this rectangle, inside this box is going to happen the refining. So, but we don't want only that part, we want also this part, this part, this part, this and this and this and this. So we're talking about 3, 4, 5, 6, 7, 8, 9, 10 boxes that we need to define. We can make this longer. How do I stretch this? How do I stretch this? Apparent midpoint. I don't know where else. Perpendicular, yes. Snap, yeah, okay. This box and this box here. So rectangle, let's draw another rectangle. Here's one and here is 0.2. 0.2? I don't think that is necessary. 0.1 would be enough because the flow is not going to be that high. So rectangle 1 and 0.1. Yes, that's what I want. So we need the coordinates of these 11 boxes, but these are not only this is we are doing 3D space. So how do we do that? So we go to our case system, SnappyHexMeshDict, and make it clear, C++. As you saw, we commented out this part, these refinement boxes, because I did it already. So what did I do? So first I have a refinement box 1, type searchable box. So it's going to search between a min and a max. So what is our min? We have this coordinate here. Let's check it. From 2.0 and 0.9. Let me change the annotation style. And we have this one here, for example, 2.2 and 1.1. So those are going to be our coordinates. Our mean coordinate will be 2, 0.9, 0. So we define that here, 2.90, and it goes to 2.2, 1.1, and our dimension, that is 0.52. So as you can see, 2.2, 1.1, and 0.52. So we do the same for all these boxes. It's a little bit tedious, but we have more control over the area. We want more resolution, cells that are smaller. So you do that for your case. As you can see, I did that already. So refinement box, refinement box, refinement box. I call this crest in this part to differentiate. So we have to define those boxes, but we need to tell the SnappyHexMeshDict what to do with them. So we go back here. First, let's change this surface refinement to 0 again. So we are not doing any surface nor edge refinement. We are doing this refinement regions. Let me take this out. So you need to put here the name of those refinement boxes. So you start with refinement box 1, refinement box 1, mode inside. You can repeat what inside does. Level is only one entry and only the level is used. All the cells inside the surface get refined. So that is what we want inside the surface. So as in surface refinement, we set the levels to 1 and 1. So it only applies one level of refinement. So what else? What we do? We will need to do this for each box we have. So one for refinement box 1, refinement box 2. So luckily there is a way to use wildcards. So that's what I erased before, and they work like this. So you need to type with this the name that all the refinement boxes start with. In this case, refinement box, and a dot and an asterisk. So it's going to read 1, 2, 3, 4, 5, everything that you have above. And as I created another box that was called crest, doesn't start with this, I need to define the crest, the same mode inside and the same level. So it's ready to run. SnappyHexMesh. We save this file. We go to our case directory and we open the terminal WSL and we run SnappyHexMesh. So it finished. It took, well, we're going to talk about that later. Let's first see the results. Our results. So we activated layer, surface with edges, and as you can see, the refinement has been performed over those regions we defined. Let's see the bottom, it's okay. Let's check this side, it's okay. Things like this happen, don't worry. Let's run a check mesh. Now I don't get it wrong, I just check for the latest time. So let's put our data. This would be called box refine, and the number of cells is here. Wow, we are talking now 5,400,000 cells, way more cells. How long did it took? 144.71 seconds. The mesh number found only to 25, the same as before, a good number. So let's discuss these results. So as you saw, the worst performing model was the edge refinement one. It did what we wanted, but not perfectly. So we are not going to discuss this. So let's open the other ones. We have here let's change his name. This is the what was it? The box refine. Let's open the surface refine. This is going to be the surface one, and let's open the one with no refinement. So let's open another view, render view, and here we are going to see the surface one, and let's open another one here. No, let's do this in this render view. We're going to see the no refinement here. Let me make this smaller. I cannot do that. I don't want to close it because I don't know how to bring it back. Sorry. But I think it's enough. So let's see. So let's zoom in the steps. This part here. Wait. This part here. And wait. So you see the results of the different methods. We have the non-refined one that is composed with cubes of the same size. The surface refined. And the box refined. So in terms of time, you can see that it's going to take longer for this model, logically, because it's going to have more cells, but you would want to use this because it's going to capture better the flow what you want. I don't want to talk about this now. I just want to show you the results, and so you can decide which one to use. So for the purpose of this video, I think this is enough. You have here a visual example, so you can define which type of refinement you want. We have not talked about snap controls nor at layers controls, especially because we are using an structured mesh. So as you can see, this is composed of all straight angles, so it's not a complicated geometry, but still those are the results. So this would be the video. So thank you for watching. This is going to be a long one.